When we talk about mixtures in chemistry, we often talk about two types, homogeneous mixtures and heterogeneous mixtures, and we talk as though those are the only two types. And the characteristics of them are homogeneous mixtures are things mixed at a molecular level, and things that are heterogeneous are bigger groups, so there's distinct areas of separate groups of the different components. Okay, that's a little vague. Examples are for homogeneous mixtures would be something like sugar water and salt water. Examples of homogeneous mixtures, and they're the only type of mixture where you can truly use the term solute and solvent. In a heterogeneous mixture, you have larger globs of particles that are all of one type, and examples of that would be oil and vinegar. Like when you make a salad dressing, you can shake them up and get them somewhat mixed, but they tend to separate out into their distinct groups. Another example would be sand and salt. When you mix them, you can still see distinct units of sand and salt, and you don't talk about a solute or a solvent. But it turns out that there are some things that are in between the two. And so that's a third type of mixture, and that is known as colloids. And they tend to be somewhat in between the two other types. Okay, so they have, one way of describing it is to say that they have groups of solute-like molecules. So not single molecules, but groups of solute-like molecules in a solvent-like substance. Okay, so instead of individual molecules mixed on a molecular level, like a homogeneous mixture, they are in groups. They're suspended, and they don't tend to settle out like oil and vinegar and other heterogeneous ones would settle out. Okay, what are some examples? An example is milk. Another example is fog. All right, and what are some characteristics, or what's familiar about this? Colloids tend to be in-between sized groups, and one thing that's familiar about this size is that the colloid size is somewhere near wavelengths of light, so they scatter light. Okay, so this size is about the size of wavelengths of light. And we're going to put lambda for wavelengths. So that's what's familiar about the size. It has a couple of important effects. One of them is called the Tyndall Effect. And that is where the particles actually scatter the light. That's the Tyndall Effect. Because of that, colloid mixtures are not see-through. Okay? They're not clear. They're not see-through. So like salt water, which is homogeneous, you can see through, and sugar water you can see through, but milk and fog you can't see through. And that's because the particles in the colloid are of the size where they will scatter light. All right, another effect of this size particle is referred to as Brownian motion. If you are able to look with a magnifying device at the particles, the colloid particles, you'll see them moving around what appears to be erratically. And that's because they are of the size where you can see the particles, like in milk. You can see the globs of the milk particles And they move around erratically because the smaller molecules are bouncing into them, but you can't see the smaller molecules. You can only see the effect they have on the colloid. So the colloid seems to be erratically moving around while smaller molecules are colliding with them. Which you can't see. So that's a little bit about colloids, which again is somewhere in between homogeneous and heterogeneous mixtures, and they are not see-through. They're going to be things like fog. That's why fog, you can't see through it. It's got the particles of water are bigger than individual molecules, so you can't, it reflects light. And in milk, you also can't see through it because the particles are big enough that they reflect light.